style in the applied sciences was to strive to solve the problem exactly. And that is what Grundle did through the work of his first PhD student to use the boundary layer idea. That student's name is Blasius. Blasius published his PhD thesis, so everybody knows the so-called Blasius solution. It is for the flow field, U as a function of x and y. Here is y and x. And like that, the velocity profile is, we know these things from scale analysis. At the location x1, downstream, it would be the same u infinity, but the profile would be stretched more in the vertical direction because the delta is bigger. So at the location x2, the picture changed, but the character of it did not change. These two, meaning the shaded, whatever you call these things, they look like knives. They are not geometrically similar according to Greek geometry, but they have the same character. They have the zero speed at the bottom, free stream speed at the top, and the curve, this is key, has only one knee. You see that? And this is the hint or the feature that empowers the analytical modeler to make an assumption and move on. And the assumption was exactly what I said, which is that these profiles are similar as if every single one at every x came out of something that you could stretch, like one of these old wrist, bands for the wristwatch. You can stretch it. It looks like this. If you don't stretch it, it looks like this. If you stretch it. So this template, the unstretched object, which is one template, is expressible as a function of a function called the position vertically divided by the thing that stretches, called delta. Delta is a function of x. And on the abscissa is the template profile, which is u over u infinity. Get it? This curve is called f prime of eta. So f prime of eta is the similarity velocity profile. Here the word similarity refers to this theory, period. It doesn't refer to the concept of similar triangles or similar hexagons. It's more like similar faces. You're talking about the two of us, Sarvesh. We're similar because we have you have two eyes, I have two eyes, okay? Same with the nose and the other features. But we're not identical, you see. would be identical with all the features if we're practicing Greek geometry or plagiarism. There you have there you have unabashed symmetry, similarity. Okay, so what do we do now? Armed with this kind of new notation, well, we go to the two equations that we've solved already, namely mass conservation and momentum. And momentum in the boundary layer region. The momentum equation in boundary layer theory is only one, because you have to use the momentum equation in the y direction to conclude that the pressure is uniform in the boundary layer. So there's only one momentum equation, which is u du dx plus v du dy equals nu d2u dy2. The next move, I tell you, these people from the antiquity of 100 years ago were actually very clever, meaning making moves, correct moves, in order to make their work easier and easier. At this stage, they introduced a concept from the 1800s called stream function. It is a function of x and y. It is itself a field. You can have a pressure field in this region, a temperature field, and a stream function field. This stream function is defined by two expressions, namely, for this particular problem, u is the partial derivative with respect to y, and v is minus partial psi dx. And this is a trick. The reason for inventing this new language called stream function is so that any value of this stream function satisfies the mass conservation equation identically. You can just substitute, and you find that this equation becomes d2 psi dx dy, and then the other one is d2 psi y dx. Get it? So you have a choice. The choice of working in the u and v notation and using two equations, or working in terms of psi and only the momentum equation, in which you substitute this partial derivative for u, and then some other derivative, obviously, for the. In fact, I'm not going to go through these details, but you can get the idea that for u, you get d psi dy. For du dx, you get d2 psi dx dy. And then here you have minus d psi dx for v, and the other one is d2 psi, and then dy2. And on the right side, you get mu, and then d3 psi dy3. Read the textbook, the 4th edition. And if you go in this direction and the with this idea in mind, now you see where this lowercase f comes into, or how it came into play. You discover that this psi that you assume must have the form u infinity nu x to power 1/2 times a function called f of eta only. So now f without prime, f is the stream function profile or similarity stream function. You can make a sketch of this stream function. We'll do that next time. And then from the stream function written this way, you can deduce several things. For example, v from here, v is turns out to be 1/2, and then nu u infinity over x to power 1/2, and then eta f prime minus f. Here, u, little u, in fact, from over here, is u infinity, and then f prime of eta. We still have one equation to solve, which is the momentum equation. When all these, let's call them substitutions, or items of language translation are substituted in the momentum equation. The momentum equation in similarity formulation reduces to 2f triple prime. Remember, triple prime comes from over here. And then plus f double prime equals 0. This f times f double prime is the short result of everything that was on the left-hand side. And then boundary conditions. How many boundary conditions do you need? In this case, for ordinary differential equation of order. So you need 3 boundary conditions. Never forget this. It's just like how many equations do you need if you have 3 unknowns? Hint, 3. In this case, boundary conditions, 3. And those boundary conditions, I'll write them in order. First of all, this speed must be 0 at the wall. And that means f prime has to be 0 where eta is 0. So the no stick v must also be 0 at the wall, because the wall is impermeable. So if these things are 0 at the wall, then f must be 0 at the wall. And what made the problem difficult was that the other boundary condition is, in fact, obvious in the entire theory, but it is not at the wall. It is far from the wall. It is in the drawing that I erased. At large enough eta, which means eta much bigger than 1, that is known as eta going to infinity according to the mathematicians. This f prime must be approaching 1, so that little u approaches u infinity. So f prime, we've all been to school, right? We know how to read something. and this something here, 1, 2, 3, tells you how to imagine the drawing that I erased, the drawing of the similarity velocity profile. But these people back then, this is early 1900s, they have no idea, even if they start their thinking from this location, this way, which is correct, they have no idea that the curve that began from their pencil and paper would end up having a slope of 1 at far away from the wall. And the so-called technique of shooting correctly, in other words, you can start this way, and this way, and of course this way. The technique of shooting correctly is known as the shooting method, and it is the one that takes you here to 1 and 1 and gives you the correct profile for the longitudinal velocity component. In other words, what was unknown, if you start from the 0 and 0, was the curvature of the curve at the origin. So that curvature at the origin is known as f double prime at eta equals 0. This was something that the problem solver had to guess and guess again, so that the curve far away would end up with a slope of 1. You see, next Monday, you learn that the correct guess was 0.332, and meaning a number of order 1. You are not impressed, and you shouldn't be, okay?